Hello class, this is lecture 6A, soil fertility, and we're focused on nitrogen for this lecture. And in this video we're going to identify how commercial fertilizer labels identify nitrogen content. We will review the nitrogen cycle with an emphasis on soil fertility. We'll identify and describe some conservation practices that reduce nitrogen pollution, and we'll discuss the Des Moines Waterworks lawsuit and the issues at hand. All right, now before I move on, we have this kind of generic 10-10-10 bag of fertilizer, and I want to point out for our first learning objective that whenever you're looking at a commercial fertilizer bag, there's always three numbers, and the first of those three numbers on the far left, this is the nitrogen content, and it is expressed as the percent of the bag that is nitrogen. So it's not any special form of nitrogen, it's just straight up nitrogen. So what percent of the entire bag is nitrogen? And in this case, 10 means it's 10% nitrogen, and so a 50-pound bag of 10-10-10 would include 5 pounds of nitrogen. Alright, so nitrogen, it is a critical component of proteins. Some examples are enzymes, nucleic acids, chlorophyll. So all these, as you can imagine, all these things are incredibly important to plants in particular, especially chlorophyll. And nitrogen is one of the most limiting nutrients, and is generally one of the most commonly used compounds beyond carbon within a plant. So if a plant is deficient in nitrogen, because it is so important for so many parts of producing a plant, plants that are deficient generally exhibit yellowing or light green colored leaves. They will have stunted growth because they can't produce enough proteins and chlorophyll to actually produce more biomass. And they oftentimes have thin, spindly leaves. And plants will take up nitrogen mostly in two forms, nitrate and ammonium. They can take up dissolved organic nitrogen, but this is in very low amounts. So generally like 1% or less of the nitrogen that's taken up by plants is small, soluble, dissolved organic nitrogen. The vast majority is nitrate and ammonium. So we reviewed the nitrogen cycle previously this semester, and we kind of gave a general overview. Now we're going to review it again, but we're going to have more of an emphasis on soil fertility. So first, let's talk about nitrogen fixation. So here we have nitrogen fixation over on the right side, and this is where we have microbes that form a symbiotic relationship with plants generally, or in some cases just microbes living on their own, but they convert nitrogen in the form of nitrogen gas into gas, and they convert that into ammonia. And that ammonia is something that the plants can actually use. The most common agricultural example of these nitrogen fixing microbes is rhizobia, or our rhizobia. So rhizobia form a symbiotic relationship with legumes, and they take atmospheric nitrogen into gas, along with hydrogen and electrons. And these electrons they are getting from them metabolizing sugars that are being provided to the microbe from the plant. So it's getting energy essentially. And so nitrogen, hydrogen, energy, the end result is ammonia and H2 gas. And this is performed inside of these nodules by the rhizobia using an enzyme called nitrogenase. So nitrogen, genase means it's a generating enzyme. It's a nitrogen generating enzyme. And ammonia can be used by the plant for its life cycle. So if you have a soybean that has rhizobia nodules, then the soybean can use all the nitrogen that the rhizobia fix to produce a soybean crop. And then at the end, there's likely some nitrogen left over, and the ammonia and all the other nitrogen that's that's locked up in the residue can then be decomposed from organic forms back into mineral forms, and then become available to plants later on. So that is how nature does it. Now, scientists and engineers have developed a way that we can actually take nitrogen from the atmosphere and turn it into forms of nitrogen that we can use at an industrial scale for our own purposes. And that is done primarily through the Haber-Bosch process. So Haber is the guy on the left, and Bosch is the guy on the right. Haber was a professor at some university in Germany, and he developed a way on a lab bench scale to take N2 gas from the atmosphere and turn it into ammonia. And then Bosch worked at BASF and scaled it up to eventually produce ammonia gas at a industrial scale. So we call this the Haber-Bosch process. And it's a very energy intensive process, and generally nitrogen is in lockstep in terms of costs with energy prices because this process is so energy intensive. It's not always the case, but generally that is how the costs work. Now, prior to this, the primary source of nitrogen that people would use on a large scale was nitrogen, which is a mineral that includes nitrate. And this was the primary form of nitrogen that would be mined and then applied to a field as an external source of nitrogen. Other than that, the only source was leguminous crops. And so, one thing that nitrogen is also used for is building bombs. And the reason that these two German scientists and chemical engineers were so interested in developing a process where they could actually create their own nitrogen from atmospheric nitrogen into a form that they could use is that this energy intensive process creates a very energy rich compound, namely anhydrous ammonia, and this ammonia it could be used for creating explosives. And so back in the World War I era, there was a blockade on allowing any import of nitrogen to Germany. And so this blockade made it impossible to get nitrogen into the country to make ammunition. And so what ended up happening is they invented the Haber-Bosch process. All right, so sort of a little history connection there to something that pretty much all of our crops rely on to this day. All right, the next part of the nitrogen cycle is mineralization, and that's where we have an organic form of nitrogen. So here we have organic material, and we have this arrow going to ammonium. So organic material being decomposed by microbes, converting it into ammonium, and this would be a biological process. So mineralization, we are mineralizing or breaking down and converting organic forms of nitrogen, like you see here, into mineral forms, namely ammonium, which the plants can then use. Because plants pretty much only use nitrate and ammonium. So some organic forms of nitrogen include manure, which can be spread or injected. Could be green manures and cover crops. Could be compost. Could be wood chips, or pretty much anything that's carbon-based that's applied to a soil. Those are organic forms of nitrogen. So that's the mineralization process, taking organic forms, allowing the microbes to decompose it, and then adding that to the soil and releasing ammonium. Immobilization is the opposite. So if there is a organic compound or organic residue that's added to the soil but is very nitrogen poor, then the microbes will immobilize nitrogen and basically remove all the nitrogen that is dissolved in the soil and and incorporate into their bodies while they decompose the organic matter. And once they're done decomposing that organic matter, then it gets mineralized again. So that is the immobilization process. And then we have absorption of ammonium. So ammonium is a cation, and so it can be absorbed on the cation exchange. And so this is a physical process. There is no microbes that are mediating this. And one thing that's nice about ammonium absorption is while that ammonium is absorbed, it cannot be lost as ammonia, which can off-gas into the atmosphere through ammonia volatilization. So this is one way that we can lose nitrogen from the system, but that ammonium, if it's absorbed, will not volatilize. And volatilization occurs when we have soils with particularly with a low CEC, but it can happen in any soils. But it's more pronounced at a high pH and at high temperatures. So pH is over 7.3, and the warmer the temperature, the more likely it is to occur. And it's this reaction here. So they have ammonium and hydroxides, which goes through this reversible reaction to water and ammonia. And this ammonia is a gas, and so if this reaction occurs and it goes to the right, then the ammonia can off-gas to the atmosphere. All right, next up is nitrification. And so anytime we have ammonium being added to the soil, nitrous ammonius and nitrobacter immediately go to work and convert it first from nitrous ammonius. Nitrous ammonius converts it into nitrite, and then nitrite is converted by nitrobacter into nitrate. And this occurs in oxidized conditions because we're adding oxygen to the nitrogen, so we have to have oxygen present. And then the next step beyond that is denitrification, where we have nitrate, which goes down this pathway under reducing environments, where it's going to go into nitrite, nitric oxide, nitrous oxide, and then dinitrogen gas. And these last three are all gas forms, and nitric oxide and nitrous oxide are both greenhouse gases. So these are not, ideally these are not things that we don't want to build up in our soil too much, because they are very potent greenhouse gases. But this all happens in reducing environments, and reducing environments occur in all soils. So it can be, could be just a normal, well-drained soil, but if you have enough moisture just coming from rainfall inside of some of the aggregates, we will have reducing conditions where denitrification can occur. But if we have a soil that's completely waterlogged, then it's going to occur at a much faster rate, and we'll lose a lot more nitrogen. So we're converting this dissolved nitrate form into gaseous forms that can off-gas into the atmosphere. So it's going, and what's happening with this is the microbes are using nitrogen as a alternative electron acceptor. And so the microbes are consuming organic matter. As they do so, they are producing all these electrons, which they need to add to an electron acceptor to get rid of the electrons. So normally they would do this with oxygen, but in the absence of oxygen, they switch to alternative electron acceptors. And if you look at the redox status or the oxidation status of each of these forms of nitrogen, in nitrate, nitrogen would have a +5 charge, and then as it goes to nitrite, it's adding 2 electrons, and it goes to a +3, and add another electron, goes to +2, add another electron, +1. Eventually it gets to dinitrogen gas, where there is no charge. So it's just N2 gas with a charge of 0 for the nitrogen elements. All right, so again, each of these steps are performed by heterotrophic bacteria under anaerobic conditions. So these are microbes that are consuming organic matter, and this occurs under a low oxygen environment. So it is decreasing the valence state of the nitrogen as more electrons are added to the nitrogen. And again, nitric oxide and nitrous oxide, that can cause nitric acid to form acid rain. And NO and N2O, I should say NO and N2O, are both greenhouse gases. And N2O can also destroy the ozone layer. So there are some environmental issues associated with those forms of nitrogen. And N2O, sometimes called nitrous or NOS, which is used in cars to make them go fast. All right, so denitrification in terms of soil fertility is a problem, because if we have a field where maybe there's a low spot where it's a little more wet, or maybe it's the whole field in a very wet year, then we have lots of denitrification occurring. And as it occurs, there is nitrogen that the farmer has paid good money for, and it is being lost. And as it's converted into gas and off-gassed into the atmosphere, that's money lost, essentially, because more nitrogen has to be applied later to make up for that lost nitrogen. So in dry soils, it's usually nominal, so small amount, so 5 to 15 kilograms, or 4.5 to 13 pounds per acre per year. And in wet soils, it can be significant, so it can be as high as 54 pounds per acre per year in wet soils. So this is actually one reason why wet soils along a stream or in what is or used to be wetlands do not make for very economical pieces of land to farm, because it does take so many inputs to actually get a decent crop. So you'd have to put a lot of nitrogen there repeatedly, which costs a lot of money in order to get the same type of yield that you get on the rest of the field. So you don't get as much return on an investment for farming wetland areas or areas next to streams, partially because of denitrification. So oftentimes those areas are targeted to take out of production by putting them into riparian buffer strips, or by putting them into some sort of wetland reserve program. All right, now one thing that can also happen from nitrate is it can be leached. So nitrate is very soluble, and as water percolates through the soil, it's going to pick up any dissolved nitrate with it and move that down through the soil in the process. And one way, or that's a concern, because nitrate is a pollutant for both drinking water and just general water quality. So it can cause blue baby syndrome or hemoglobinemia if it's consumed by babies, and it's also somewhat of a cancer concern for everyone else if you consume nitrates in a large amount. So there is a limit on how much nitrate we can have in drinking water, and so we want to use practices that reduce how much nitrate is lost from agricultural fields. Now, one way that we can do that is if the nitrate is no longer able to be used by the crop, say if it leached and then went to a nearby stream, one thing we can do is actually create a man-made wetland by damming up that stream. And in the process, we have this very wet environment where all the soil is saturated, and we can encourage denitrification. So we have nitrates flowing into a wetland. That wetland's going to hold onto that water for a while, and it's going to result in the denitrification of nitrate into nitrogen gas. So this is a great way to improve water quality and drinking water quality. And one program that's used to do that is the Conservation Reserve Enhancement Program. So you've probably all heard of the Conservation Reserve Program, where marginal lands are taken out of production, and subsidies are provided to the farmer to keep those lands out of production for 10 to 15 years. In the case of CREP wetlands, it's the same process, but there's a wetland that's constructed on the property with the primary goal of providing both habitat and also improving water quality. So here's a couple of pictures from CREP wetlands in Minnesota. Buffer strips are also a common practice that are focused on removing nitrate. So if we have water that has leached out of the root system of the upland crop, so further up the hill, then eventually that water is going to work its way towards the stream. And if there's a buffer strip along the stream, then the plants growing on this buffer strip, whether that be trees or grasses, those plants can use that nitrogen before it reaches the water. The plants can also exude carbon, which acts as a food source for microbes, which can, in this anaerobic environment, denitrify the nitrate that is in the water. So it's both taking up nitrate and also facilitating denitrification. And in the process, it provides habitat. And in addition to all this, the areas along streams are generally very wet. And so because denitrification would occur anyway, economically, it doesn't make the most sense to try to treat these soils the same as we would the upland soils. And so in some cases, it might actually be to the farmer's economic advantage to take these lands out of production and use them for creating habitat and cleaning water. Another practice that is recently emerging is contour buffer strips. Or guys, contour buffer strips have been along for a while, but contour buffer strips, in terms of prairie strips, are becoming more widely accepted and more commonly used. So a contour buffer strip is where we have contour tillage or contour farming, where all the rows are planted in a contour around a hill. And if we have strips of grass in between these strips of row crops, then the grass can help slow down the water that's flowing downhill. And that slowing the water can trigger more infiltration, which reduces runoff and also reduces how much erosion can occur. But what can also happen is if we have less runoff, we have less nitrogen loss so we have some nitrogen that's in the runoff water, and if it runs off stream, that nitrogen will eventually go into the stream. But if that water is instead infiltrated and could be used, and the nitrogen could be used by these crops or denitrified within these contour buffer strips, then we're going to remove some of that nitrogen export that might have happened in the soil otherwise. So contour buffer strips are a good conservation practice that accomplishes some of the same goals, removing nitrogen or preventing export of nitrogen from the farm. We can also use cover crops for managing nitrogen. So legumes can add nitrogen to the soil. So that's one of the more common reasons why legumes are used in crop rotations. But if we have a leguminous cover crop, that means that we're adding nitrogen to the soil during a time of the year when the soil and the land isn't being used to create a cash crop. So just by protecting the soil with a cover crop, we get value added by actually having that cover crop fix nitrogen for us. In terms of non-legume cover crops, these don't add nitrogen to the system, but these non-legume cover crops, so ryegrass, for example, or just any kind of grass, these grasses can take up any of the existing nitrate that's in the soil, incorporate it into the plant's biomass, and then prior to the planting and establishment of the next cash crop, this grass cover crop can be terminated. And after it's terminated, then all the nitrogen that was locked up in that grass starts to decompose, and by the time it's mineralized by the microbes, it's going to become available to the cash crop. So it prevents the loss of nitrogen in the form of nitrate. It prevents that leaching of the nitrate by holding onto the nitrogen in the biomass of the cover crop itself. So with both types, we're going to have some improvement in terms of soil erosion, so we'll have less erosion overall. And it's also going to, in most cases, increase water availability for the cash crop because it's increasing, or it's building structure and increasing infiltration, and also shading the soil during times of the year where it might otherwise be evaporating. And also we have less or more residue on the surface and less evaporation. All right, now I want to move on to a case study that's related to this nitrogen management. So back in 2015, in 2016, there was a lawsuit from Des Moines Waterworks. And so Des Moines Waterworks is the uh, the entity that manages all the drinking water supply for the Des Moines metro area, so which is about 1 million people. And so the Des Moines Waterworks, they were having this issue where they were having to filter out nitrate from primarily the Raccoon River, uh, be, because there's just such high nitrate concentrations in the water, and it's a regulated contaminant. So the EPA doesn't allow nitrates above 10 parts per million, or 10 milligrams per liter, for drinking water. And so this facility that you see on the right, these are resin tanks. So these are about 2-story tall resin tanks, and I've actually toured this facility. But these tanks have anion exchange resins in them, and so the water is sent through these tanks, and all the nitrate absorbs onto the resin, and it removes it from the drinking water, and then eventually they remove the nitrate from the resin and actually put it back into the stream, or back into the river. But the river that is the issue is the Raccoon River, and the Raccoon River exists on the western edge of what we call the Des Moines lobe. So this green area in north central Iowa was the most recently glaciated portion of the state. So it's very flat, and if you're a duck hunter, you might know this to be sort of the southern extent of the Prairie Pothole region. So back before everything was settled, there were many wetlands here, and so I grew up in Emmett County, and which is up on the top here, and there's a town about 20 miles to the east, and it was said that back when people first settled this area, you could take a canoe during the wet part of the year. You could take a canoe from my town on the west part of the county to 20 miles to the east, to the next town on the east side of the part of the county. So it was so wet because there's so many wetlands between those areas. So it's a very flat, very wet area, and now it's been mostly drained, and it's some of the most productive cropland in the world. Now, the areas that were a concern for this lawsuit were Buena Vista, Sac, and Calhoun counties. So these 3 counties, they have the Raccoon River flowing right through it, and the Des Moines Waterworks noticed that the Raccoon River was getting most of its nitrate load from these 3 counties. And so in order to try to get the counties to kind of clean up their act so that they wouldn't have to pay money to run these resin tanks all the time, they sued these 3 counties so that they'd actually do more to prevent nitrate from going into the water. And I should mention that it costs $1 million a day to run those resin tanks, so it's not a cheap operation. So this is serious money we're talking about here. So for some more context, the Des Moines lobe was once all prairie potholes, and most have been drained and turned into farmland. So in this picture, you see there's prairie potholes, and most of them are still in existence. But in most of that part of Iowa, these have all been drained with tile lines or ditches, and they've been put into crop production. So one issue with that is, instead of the soil being able to denitrify the water and remove the nitrate from the system, this nitrate is able to freely drain through the soil, going to a tile line, and it basically then has a direct route into the Raccoon River. And so here's what tile lines look like. So here's a drainage ditch, and you can see a tile outlet coming in here. So there's a tile that's draining this field over here, and all that drainage water is flowing into or flowed into this regional drainage ditch here. And these are installed using these big tile machines where they have like one big tine that pulls its way through the soil, and then as that tine basically splits the soil, a tile line is put behind it and is inserted behind it, and then the soil is closed off behind. And so you can see what a drainage pattern would look like in a newly tiled field. So they're just going through basically below each of these what used to be Prairie Pothole wetlands and putting in these tile lines to drain the soil. All right, so on the Des Moines Waterworks side, their argument was that they have to meet the federal drinking water standard. They have no choice but to filter out that nitrate to provide safe drinking water to the citizens of the Des Moines area. And they get their water from three sources, but the Raccoon River is the primary source. So they also pull water from the Des Moines River, and they also pull water from groundwater. And when they can, they try to dilute the Raccoon River water with the other two sources to bring that water, the concentration of nitrate in the water down to 10 parts per million. But when they can't, they have to send it through the resin machine, or the resin exchange system, and that costs $1 million a day to operate. And they've also argued that the counties upstream have made very little progress in terms of reducing how much nitrate pollution occurs. So there's, so I've driven through this area a lot, and I've spent time there as well. And there is very little use of cover crops, and there are other management practices that could go a long way. So cover crops is one. Only fertilizing in the spring rather than fertilizing in the fall, and also constructing wetlands and adding riparian buffer strips. These are all things that would greatly help to reduce how much nitrate pollution there is, but the county doesn't really follow those things. So as a whole, and I can attest to that myself, just actually going through there. So it costs $1 million a day to run that filtration system. And so the consumers that are consuming the drinking water are forced to pay all these additional costs, but they're not the ones that are polluting the water. Now, on the other side, the county and farmers, so the county and the regional water management districts and the farmers, their argument is that the Des Moines lobe soils are naturally very fertile, and that there would always be mineralization of organic matter that would cause high nitrates in the water anyway. And they also can't control the weather. So when the corn grows, where it's using the most water and using the most nitrogen is in June and July. But if there's heavy rains prior to that, then all the nitrate that's in the soil can get washed out. So that's when we get a lot of leaching that occurs. And also, in order for them to get the optimum corn yields, it requires a lot of nitrogen. So they can't apply just a small amount. They have to apply a lot to actually get those optimum yields. And they claim that management practices that limit nitrogen leaching would also potentially reduce yields and farm income. So for some context, one thing I drive by when I go back to my hometown is the Nutrien Early Distribution Terminal, which is the top two pictures here. So I just took these pictures just driving by on one of my trips through that part of the state. And then also across the street is a confined animal feeding operation. So this is one of the biggest hog producing areas of the world as well. So there's lots of animal waste. There's also lots of chemical use. And I was driving through here. I've seen times where people were applying manure or spreading manure on frozen ground, which is illegal. And I've also seen lots of anhydrous ammonia being injected on fields in the fall, whereas if they wait till spring, then there's a lot less chance of leaching of the nitrates. But yeah, so there's definitely a lot of work that could be done. Now, backing up, for the big picture, in the last 50 years, pretty much all the crops that aren't corn and beans have disappeared. And as a result, there isn't a market for any other crops. So the only markets are really to take your grain to the local elevator, and the only things you can really market there are corn and soybeans. So there isn't as much demand for say forages. There's not demand for other cereal crops or vegetables or anything. Like the only really two things in the show there are corn and soybeans. And as a result, on a watershed basis, there's really very few plants that are growing in the early part of the spring. So the entire watershed is pretty much all corn and bean fields. And the result of that is early spring or early summer, there's very little plants that are growing, and it makes for a very leaky system because all the rainfall is just going to leach through and it washes away all the nitrogen. But the soils are warm enough where the microbes are still active, which means they're going to be converting ammonium into nitrate. And as it's converted into nitrate, it's able to be leached out of the system. So the end result is we get a very leaky system. Now for the outcome, the lawsuit was eventually dismissed. In other words, the counties won and Des Moines Waterworks lost. But what it did do is put Iowa water quality and farm production practices under the spotlight. So now it's a regular discussion in newspaper stories and just news in general in that part of the world on how poor the water quality is in the state of Iowa. One interesting thing that happened is the Storm Lake Times. So Storm Lake is one of the bigger cities within this area. So Storm Lake, the Storm Lake Times editor won a Pulitzer Prize, and he investigated the source of money that was used to pay for the defenses of these counties. So there were millions of dollars that were brought into these counties to pay for the defense team for this lawsuit. And these counties are public entities, and no one knows where they got the money to actually pay for the defense team to defend their side of the lawsuit. And even with Freedom of Information Act requests, no one is able to ever ascertain where the funds came to pay for the defenses of these counties. And so he did a bunch of investigating on that and eventually won a Pulitzer Prize. And he's almost sort of a news celebrity, I guess you could say. So especially every 4 years when there's a presidential election, all the candidates like to go to him to get more publicity and kind of get a feel for the state. And then other reporters talk with him as well because he kind of has his thumb on just politics of Iowa in general. But anyway, it's kind of an interesting outcome. Now, I've also heard that the lawsuit will be filed again. So Des Moines Waterworks is gonna come back at it with a second try sometime in the near future. So we'll have to see how that turns out. Now, in terms of improving the water quality, there are ways that this problem could be fixed. So one could be expand the use of winter cover crops, and also the use of more timely nitrogen fertilizer application would help a lot. So right now, most of the nitrogen that's applied is injected as anhydrous ammonia in the fall. If that anhydrous ammonia injection were to happen in the spring, then there's less time for all the ammonia to be converted to nitrate and leached out. So there's just less chance of leaching to occur if it's injected in the spring. So delaying nitrogen application to the spring would be a huge advantage, or be a huge help. Also, if they can install riparian buffer strips along the streams and ditches in those counties, that would help encourage denitrification and improve water quality. And also installing crepe wetlands to denitrify the nitrate that's in the streams would go a long ways as well. And also, if there was more integrated agriculture practices, for example, if there were more cattle that could consume more forages, then that would mean that there would be a larger portion of the landscape that is being used for growing plants other than corn and soybeans. And so those forages would help kind of take certain parts of the landscape or the watershed out of the area that's potential nitrate sources. And so if there's less that's just straight up corn and beans and more that goes into perennial crops like forages, then that would kind of help with the early and late season losses of nitrate. So in this case, integrated agriculture might be a good solution. So now what I want you to do is, in a graded discussion for class, I want you to discuss your thoughts on this complex court case. So if you were the judge, I have two questions for you. First is, if you were the judge in this case, whose side would win and why? And also, what do you think would be a reasonable win-win scenario where both sides of the issue could come out better off? So is there a way where both sides of the lawsuit, instead of actually taking court action, is there a way that they could work together to improve the water quality and improve the drinking water quality for the Des Moines area? So let me know your thoughts on this and post that in the discussion. So I'm going to wrap this up with some just general recommendations for nitrogen management. We only want to apply the amount of nitrogen that will be used by the plants. So this is known as the agronomic rate. So we can only apply what is agronomically feasible and required in order to produce our crop or produce a lawn that we're trying to grow or what have you. We also want to limit the time the nitrogen is applied and the time where the nitrogen is demanded by the plants. So back to that Iowa example, most of the area is corn, and the biggest demand for nitrogen in corn is in the month of July. And so the closer we can get to application of nitrogen to July, the better. So that could be side dressing corn once it's already emerged, or applying just before the season starts, or something like that. So we're trying to limit the amount of time between application and nitrogen demand. We can also use cover crops to conserve nitrogen for next year's crop. We can use legumes to increase soil diversity and to get some free nitrogen. And also, we want to be cognizant of the organic matter applications. So we want to apply enough phosphorus demand and supplement the mineral nitrogen as needed. And also, we want to test our